Picture standing on Earth exactly one day after the asteroid hit, not a metaphor. An actual single day, 66 million and 1 year ago, give or take. The sky is still choked with ash and vaporized rock, hurled so high into the atmosphere that sunlight can barely reach the surface. Wildfires are burning across entire continents, ignited by a hail of superheated debris that rained back down from orbit within hours of the impact. The oceans are acidifying. Roughly 3/4 of every species alive on the planet just days earlier, including every single non-avian dinosaur, every massive marine reptile, every flying pterosaur, has been wiped from existence in a geological instant. This is the world the Cenozoic Era inherited, a scorched, dust-choked, ecologically gutted planet with almost nothing left standing at the top of the food chain. And what happened next, over the following 66 million years, is one of the single greatest comeback stories in the entire history of life on Earth. A slow, staggering climb from ash and silence all the way up to whales the size of buildings, mammals bigger than elephants, ice ages that reshaped entire continents, and eventually, improbably, us. The very first stretch of this new era, called the Paleocene, running from 66 million years ago to about 56 million years ago, doesn't look like the triumphant beginning of the age of mammals that popular imagination tends to picture. It looks like a slow, cautious recovery from a planet-wide disaster. In the immediate aftermath of the extinction, the fossil record shows a strange, almost eerie period sometimes referred to by paleontologists as a disaster fauna phase, where surviving species were disproportionately small, generalist, and unremarkable, essentially the biological equivalent of scavengers picking through the wreckage of a collapsed civilization. The mammals that made it through the extinction were, almost without exception, small, nocturnal, shrew-like or rodent-like creatures, rarely larger than a modern-day cat. Species that had spent the previous 150 million years of the Mesozoic era living quite literally in the shadows, evolutionarily sidelined by an ecosystem completely dominated by dinosaurs. With the dinosaurs suddenly catastrophically gone, and with entire ecological niches, apex predator, large herbivore, tree canopy specialist, sitting completely empty for the first time in tens of millions of years, these small, unassuming survivors found themselves facing an evolutionary opportunity unlike anything that had happened before or has happened since. The recovery, though, wasn't instant, and the fossil record makes that clear. It took roughly 10 million years, an almost incomprehensible stretch of time by human standards, but genuinely fast by the standards of large-scale ecological recovery, for mammals to diversify into anything resembling the scale and variety we'd recognize today. Early Paleocene mammals like Pantalambda, an odd, sheep-sized, plant-eating creature with a strange mix of primitive and specialized features, represent some of the first tentative experiments in mammals, growing larger and more ecologically specialized after the extinction. But it wasn't until deeper into the Paleocene that things really started to accelerate. Around 58 million years ago, in what is now Colombia, a truly staggering predator emerged. Titanoboa, a snake stretching an estimated 42 feet long and weighing more than a ton, the largest snake ever known to have existed, so massive that its sheer size has actually been used by scientists as an indirect thermometer for the ancient climate, since a cold-blooded reptile that large could only have survived in a tropical environment, significantly warmer than anything found in that same region today. Titanoboa is a genuinely useful symbol for the entire Paleocene. A world still finding its footing, still experimenting with scale and dominance, in an ecosystem where the old rules had been erased and nobody had yet firmly established the new ones. Then, around 56 million years ago, the planet underwent one of the most dramatic and best documented climate events in its entire geological history. A sudden, sharp global temperature spike known as the Paleocene-Eocene thermal maximum. Over a period that, geologically speaking, happened astonishingly fast, likely just a few thousand years, global average temperatures spiked by somewhere between 9 and 14 degrees Fahrenheit, driven by a massive, still not entirely understood release of carbon into the atmosphere and oceans, with volcanic activity associated with the opening of the North Atlantic Ocean, as the leading suspected trigger. The effects were sweeping. Ocean chemistry shifted dramatically, causing a significant extinction event among deep-sea organisms. Tropical conditions expanded so far toward the poles that fossil evidence of palm trees and crocodile relatives has been found in what is now the Arctic Circle, a genuinely mind-bending detail once you actually sit with it. Alligators swimming in polar waters that, today, are frozen for most of the year. And this marked the beginning of the Eocene epoch, running from 56 million to about 34 million years ago, which stands out as one of the warmest, wettest, and most biologically lush stretches of the entire Cenozoic, a genuine global hothouse. It was during this warm, lush Eocene world that mammals truly exploded into the diversity and scale we associate with the age of mammals today. On land, this era produced some of the strangest, most genuinely alarming predators ever to walk the planet. Andrewsarchus, known only from a single enormous skull discovered in Mongolia, is estimated to have been the largest land-based carnivorous mammal ever to exist. Roughly the size of a large bear, but with an elongated, powerful skull built for crushing bone, likely functioning as an opportunistic predator and scavenger prowling the floodplains of ancient Asia. Elsewhere, an entirely different group of predators called the mesonychids, wolf-like mammals with hooved toes, an evolutionary combination that sounds almost impossible today, dominated the mid-sized predator niche across multiple continents. But the single most remarkable transformation of the entire Eocene, arguably of the entire Cenozoic era, happened not on land at all, but in the shallow coastal waters of what is now Pakistan and India. And it's a story so strange that if it weren't backed by an extraordinarily well-documented fossil record, it would sound like pure invention. Somewhere around 50 million years ago, a group of small, hoofed, land-dwelling mammals, distant relatives of modern hippos, began wading into shallow coastal waters, likely in pursuit of food or safety from predators. Over the following roughly 10 million years, an evolutionary transformation unfolded that paleontologists have been able to reconstruct in genuinely remarkable fossil-by-fossil detail. Pachycetus, one of the earliest identified members of this lineage, looked essentially like a land mammal with slightly unusual ear structures adapted for underwater hearing. Ambulocetus, whose name literally means walking whale, appears just a few million years later. A genuinely bizarre-looking creature resembling something between a crocodile and an otter, still capable of moving on land, but clearly spending increasing amounts of time hunting in water. By around 40 million years ago, Basilosaurus and Dorudon had emerged, fully aquatic, serpentine-bodied creatures stretching up to 60 feet long, still retaining small vestigial hind limbs, tiny, functionally useless legs that serve as an almost unbelievably direct physical record of their land-dwelling ancestry, frozen inside the skeleton of an animal that had otherwise completely committed to life in the ocean. This is the lineage that would eventually give rise to every whale, dolphin, and porpoise alive today, one of the single best documented examples of large-scale evolutionary transformation in the entire fossil record, unfolding entirely within the warm, expansive seas of the Eocene world. Then, around 34 million years ago, the planet's long, warm Eocene hothouse came to a decisive and consequential end, and the reason has everything to do with the slow, grinding movement of entire continents. For most of the Eocene, Antarctica had remained loosely connected to South America and Australia, and as a result, warm ocean currents from lower latitudes were still able to reach and moderate its coastline, keeping the southern polar region from freezing over completely. But continental drift, operating on its own patient, multi-million-year timescale, eventually pulled these landmasses apart, opening two critical oceanic gateways, the Drake Passage between South America and Antarctica, and the Tasmanian Gateway between Australia and Antarctica. Once these passages opened fully, a powerful new current, the Antarctic Circumpolar Current, was able to form, encircling Antarctica completely and critically, isolating it from the warm equatorial currents that had previously kept it temperate. Cut off from that warming influence, Antarctica's climate collapsed into permanent, sustained cold, and massive ice sheets began forming across the continent for the first time since well before the dinosaurs had gone extinct. This event, known as the Eocene-Oligocene transition, triggered a documented mass extinction among many of the specialized, heat-adapted species that had thrived throughout the lush Eocene world. And it marked the beginning of a long-term global cooling trend that would define the rest of the Cenozoic era all the way through to today. The Oligocene epoch that followed, running from 34 million to 23 million years ago, is often somewhat unfairly overlooked in popular retellings of prehistoric life, overshadowed by the more famous eras on either side of it, but it produced one of the single most staggering land mammals to ever exist. Paraceratherium, sometimes also referred to as Indricotherium, was a hornless relative of the modern rhinoceros that stood an estimated 16 feet tall at the shoulder and is estimated to have weighed as much as 20 tons, making it, by most calculations, the largest land mammal ever confirmed to have existed. A herbivorous giant capable of browsing on vegetation from treetops that no other ground-dwelling animal of its era could reach. Alongside genuine giants like Paraceratherium, the broader Oligocene world was also home to Arsinoitherium, a bizarre, heavily built herbivore native to northern Africa, sporting two massive, forward-curving horns on its snout that gave it a passing, almost startling resemblance to a modern rhinoceros, despite the two animals being only distantly related, a striking example of what paleontologists call convergent evolution, unrelated species, independently arriving at strikingly similar body plans because they're solving similar ecological problems. By the time the Miocene epoch began, roughly 23 million years ago, and running all the way to about 5.5 million years ago, the planet's cooling, drying trend had triggered a genuinely fundamental transformation in what covered the Earth's land surface, and this transformation would go on to reshape the entire course of mammalian evolution. Grasslands, ecosystems that had barely existed at all during the warmer, more forested Eocene, began expanding dramatically across huge stretches of every continent, driven by the cooler, drier global climate. And grass turned out to be a genuinely difficult food source, tough, low in nutrients, and packed with abrasive silica compounds that wear down teeth at an accelerated rate, which meant that animals capable of successfully exploiting this newly abundant resource needed serious evolutionary specialization to do it. This period saw the rise of true specialized grazing mammals, horses among them evolving longer legs built for sustained running across open terrain, and high-crowned teeth specifically adapted to handle a lifetime of grinding down tough, silica-rich grass without wearing their teeth down to nothing. The Miocene also saw the emergence and spread of the first bear dogs, the amphisbaenids, powerful, ecologically flexible predators that dominated much of the northern hemisphere for millions of years, and, critically for the future of our own species, the diversification of early apes across Africa, Europe, and Asia, setting the evolutionary stage tens of millions of years in advance for the eventual emergence of hominids. Then roughly 3 million years ago, deep into the Pliocene epoch, one of the most consequential geological events of the entire Cenozoic Era quietly finished forming, and it would go on to trigger a genuine ecological revolution. The Isthmus of Panama, a narrow strip of land connecting North and South America, completed its formation, closing off what had previously been an open ocean gap between the two continents. The immediate oceanographic effect was significant on its own, rerouting ocean currents and playing a major role in intensifying northern hemisphere glaciation. But the biological effect was even more dramatic, and it's known today as the Great American Interchange. For tens of millions of years prior, North and South America had been almost entirely separate evolutionary theaters, each continent developing its own distinct, isolated caste of mammals with virtually no contact between them. Once the land bridge fully closed, animals from both continents suddenly had a direct overland route to migrate, invade, and compete with each other for the first time in their evolutionary history. The results were often brutal and one-sided. Predators and competitors migrating south from North America, including saber-toothed cats, bears, and a wide variety of dog and cat relatives, drove a huge number of South America's previously isolated, uniquely evolved native species to extinction, including many of the continent's own giant flightless predatory birds and native marsupial carnivores that had evolved in complete isolation and simply weren't equipped to compete with these new arrivals. It stands today as one of the clearest, best documented natural experiments in evolutionary biology, demonstrating in real, physical fossil evidence exactly what happens when previously isolated ecosystems are suddenly and permanently connected. Which brings the story into the final, and in many ways most dramatic, chapter of the Cenozoic, the Pleistocene epoch, beginning roughly 2.5 million years ago and running until just 11,700 years ago, an era defined above all else by repeated dramatic swings between brutal ice ages and warmer interglacial periods, and populated by some of the most iconic large mammals ever to walk the Earth, collectively known today as Ice Age megafauna. Woolly mammoths, covered in thick, shaggy fur and equipped with specialized fat deposits to survive the brutal cold of the northern tundra, roamed across huge stretches of North America, Europe, and Asia. Smilodon, the true saber-toothed cat, hunted across the Americas, using canine teeth that could grow up to 7 inches long, and recent biomechanical analysis of its skull and jaw structure suggests it likely used a powerful, precise stabbing bite to the throat or belly of large prey, rather than the crushing bite technique used by modern big cats. Giant ground sloths, some species growing to the size of a modern elephant, browsed on vegetation across the Americas, while enormous short-faced bears, among the largest land predators of the entire era, competed directly with early human hunters for territory and resources across the same landscape. This was also the era when our own genus, Homo, finally entered the picture in earnest, evolving, spreading across continents, and, according to a growing body of archaeological and genetic evidence, playing at least some significant role, alongside dramatic climate shifts at the end of the last glacial period, in the eventual extinction of much of this Ice Age megafauna roughly 10 to 12,000 years ago. A debate among paleontologists and archaeologists over the exact balance of human versus climate-driven causation that remains genuinely active and unresolved today. And that brings the story to now, to the Holocene epoch, the roughly 11,700 years since the last major glacial period ended, an unusually long and unusually stable stretch of relatively warm, predictable climate that, not coincidentally, happens to be the exact window during which human civilization, agriculture, cities, writing, and everything that followed actually developed. Many scientists today argue we've already crossed into an entirely new geological chapter, one increasingly referred to as the Anthropocene, defined not by asteroid impacts or continental drift, but by the sheer scale of human influence on the planet's climate, ecosystems, and geology itself, a proposition still being formally debated within the geological community, but one that reflects something genuinely significant about where 66 million years of recovery, transformation, and evolution has ultimately led. Step back and look at the full arc of it, and the Cenozoic Era stops looking like a simple, tidy story of mammals quietly taking over once the dinosaurs cleared out, and starts looking like what it actually was. An extraordinarily long, genuinely dramatic 66 million year saga of catastrophe, opportunity, climate whiplash, and relentless evolutionary experimentation. A scorched, ash-choked planet with almost nothing left standing slowly rebuilt itself into a global hothouse full of 42-foot snakes and land-dwelling ancestors of whales. That hothouse collapsed into ice and cold as continents drifted apart and severed ancient ocean currents. Grasslands spread and reshaped an entire continent's worth of teeth and legs. A land bridge quietly closed in Central America and triggered a one-sided evolutionary war between two previously separate hemispheres of life. And ice ages rose and fell across the northern half of the world while mammoths, saber-toothed cats, and giant sloths walked across landscapes that a small, upright walking primate was just beginning to learn how to survive in. Every single piece of that sprawling 66 million year chain of events, extinction, recovery, transformation, collision, cooling, adaptation, had to happen in exactly the sequence it did for the world to look the way it does today. And somewhere near the very end of that almost incomprehensibly long chain, improbably, here we are.